So the last designer or pair of designers that I want to look at in this sort of examination of post-war relationships between industry and design are the Eameses, Charles and Ray Eames, who are sort of best known for their furniture, but as we'll see also had ideas about architecture and sort of design culture beyond things that we normally associate with construction, but nevertheless, I think were instrumental in defining an approach to building that resonates very clearly with what Prouve was thinking about in terms of his prefabrication, taking knowledge from the shop floor to the job site, and in Fuller's more sort of fantastical ideas about how industry might transform the housing market in particular. The two of them have this kind of funny life story. Charles Eames was a native of St. Louis. He had a sort of blue-collar background, but was artistically inclined. He studied at Washington University, locally in St. Louis, and made it to Europe in 1929, which kind of opened his eyes a little bit. Ray, his soon-to-be wife, was a California native who was an artist who had come to design more exclusively through the fine arts. So Eames had experience on a factory floor. Ray had experience in a painting studio. The two of them met at Cranbrook in 1940, slightly scandalous. Charles was married at the time and was an instructor. Ray was single and a student. But they fell in love and ended up marrying in 1941. They moved to California, so probably far away from the more conservative atmosphere around Cranbrook. And they began looking at this particular material that wasn't exactly new, but was sort of newly available or newly commercialized, and that was plywood, one of these materials that we take completely for granted today, but that does have a history, and that wasn't always in our kind of arsenal of things to work with. Charles's day job was building things for the movie industry, but they, like Fuller, understood the value of good publicity, and their social circle included John Entenza, who published this very influential magazine, Arts and Architecture, which, as we'll see, was crucial not just to the Eames's career, but to many others as well. Their experiments with plywood were literally done in their kitchen. We don't think very much about the composition of this material, but it is an incredibly versatile thing to work with. It's made by taking thin veneers of wood that are basically shaved off of cylindrical logs. So you get these very, very long, very wide, thin sheets of wood. You lay those up and impregnate them with resin. You let the resin cure, and you get a very, very stiff board, as most of us are familiar with. The sort of magic of it is that while the resin is curing, you can mold the plywood into just about any shape you want if you're a little bit careful with it. And therefore, you can make curved forms that would probably be much more difficult in a lot of metalwork. We looked, for instance, at break shaping, at what it takes to curve metal panels. It's possible, but relatively difficult. Plywood, you can get these shapes a little bit more naturally. And Charles and Ray begin experimenting with a home-built machine that they call the Kazam on the left. And basically what that is it is a wooden frame with an air bladder in the middle. You can see the bike pump that they use to inflate it. They use the bladder to press uncured plywood into molded forms, and then as the plywood would cure, it would hold on to those forms. And you see one of their early chair experiments on the right. Plywood is a little bit tricky. You can see that you can't just make any form. You have to think about how it's going to stretch or how it's going to curve, and so you have to put slices in it that relieve some of the stress that builds up as it's curing. But the Eameses literally are experimenting with this in their kitchen, kind of after hours, thinking about possibilities that this new material has for design, completely home cooked. Like Fuller, like Prouve, they get commissions from the military during World War II, albeit on a much smaller scale. And they use their plywood expertise to design and manufacture these leg splints. They make hundreds and hundreds of these. And the Army likes them because they need splints for soldiers who are wounded in battle. They don't want to waste steel or particularly aluminum, materials that would typically be used for these, because that stuff has to go into airplanes and tanks and ships. So being able to use plywood for this is a big advantage. And as you can see, the Eames has designed these splints so that they can curve them while the plywood is uncured. Once the plywood is cured, they get this very, very stiff splint out of it, and they carve slots and things into the veneers so that there are places for bandages to loop over the injured leg and through the holes on the splint. Reasonably successful. They make some good money off this, but also realize that after the war, they have this technology that allows them to create complicated curved forms, and they can apply this maybe not to the medical profession, but to furniture. And very quickly, they work with the furniture company Herman Miller to design a series of plywood chairs that today you still see all over the place. The basic chair that you see on the right uses a bent tube for a frame. The ends of the tube are kind of hammered out, as you see it at the top. And then what the Eameses do is they make these two plywood shapes, one for the seat and one for the back. Those can get applied to the metal stand with some simple screws and rubber fixings that give it a little bit of play. You see on the left a version that they produced that uses all plywood, so replacing the metal frame with actual plywood legs. These chairs are incredibly simple. They're very elegant. The warm kind of texture or tone of the plywood works really well with the kind of cool steel, and they are hugely popular. And these chairs really are what make their name, and also in a lot of ways make Herman Miller sort of iconic producer, manufacturer of what we now think of as mid-century modern. On the left, you see a simple stamping device that Herman Miller developed along with the Eameses to make these subtly curved, fairly elegant shapes out of plywood. You get a sense for the kind of scale of the operation. And Herman Miller and the Eameses collaborate on all kinds of furniture, not just in plywood, but also in aluminum and in steel and fiberglass and these other materials that are coming online. And maybe their most iconic one is this lounge chair that is still in production today, where they use aluminum and steel and plywood and leather. They actually use baseball glove leather for the seat cushions. And you can see that even though it becomes this iconic, high design chair, they have broken the process down into basically about 15 or 20 pieces. They've thought about the piece of furniture in the same way that Henry Ford would have thought of the Model T, right? It's something that has to get built on an assembly line, where each piece has to get fabricated in a way that's relatively efficient. Everything has to get put together in a way that uses labor kind of wisely. But as per Prouve, as per Fuller and Noguchi, the end result has to be beautiful, right? And so there is a lot of work similar to what Prouve does on the factory floor at Meudon, where Charles and Ray Eames are constantly working with the people who run the production lines, trying to find ways to do things slightly better, constantly prototyping. There are probably more models of these chairs than there were drawings or sketches, and constantly changing things as they're being made in the factory to think about how to do it better, faster, more efficiently, but also to produce a better object at the end of the day. And their commissions, when you know what to look for, they're absolutely everywhere. So the so-called Eiffel chair that you see on the left, which you may have had in your elementary school gym, but also with a different base, can function as a very elegant dining chair. And on the right, the waiting lounge furniture that most of us have sat in the world's airports, which are made out of cast metal and leather for the sling back and seats. This is not only a very successful business, but also a very lucrative business. And the Eameses use the income from their Herman Miller commissions to start a design office in Venice Beach in California. And this becomes one of these places that all sorts of important figures emerge from. The cast of characters who pass through or who work in this office are numerous. And they're basically interested in everything. They see the entire world as a kind of design problem. And you see on the left, this is their sketch of how they want to practice, right? That there are interests that the design office itself has, there are interests that the client has. These are combined. The big bean shape is the interests of or concerns of society as a whole. And the Eames want to work in the center. They want to work at the overlap of all of these interests. They see themselves as a laboratory. The clients, of course, have problems that need solutions. Everyone agrees that there are certain things about society that need fixing. If the Eames can find places where those overlap, that's where they want to go, right? That's what they want to basically dive into. They are ecumenical in their approach. They see themselves as just kind of general designers, and the work they do ranges from photography and film to furniture design to, as we'll see, architecture. Anything that involves kind of the application of cleverness, I guess, they are interested in. And they're also great collectors. You see in the office walls that they have just found things like typeface letters that they've plastered up on the wall as inspirations, collages of photographs of things that they've seen. They have this incredible kind of energy and a real sort of joy in their approach that becomes the signature of the office. John Entenza is a publisher, and his magazine, Arts and Architecture, is profoundly influential in reaching kind of progressive architects, but also potential clients. It's the sort of quintessential mid-century modern design journal. He commissions in 1944 the Eameses to talk about the prefabricated house. The end of the war is on the horizon. Entenza, like Fuller, like Prouve, sees that the big question is going to be how to take the industrial capacity of the Americas and to turn it to this incredible problem that everyone knows we're going to face, which is housing this demographic boom of the 1940s and 1950s. And the Eameses basically say, look, this is a design problem, right? Housing is a design problem writ large, and the way to approach it is to be a little bit of an economist, a little bit of a scientist, a little bit of an anthropologist, a little bit of an engineer, and to think about how to apply all of these resources that we have, mass production, to the what we know about how these families are going to work, right? And on the right, you see a diagram that could come, I think, in some ways, right out of Darcy Thompson, right? An understanding of family behavior, how the house has to perform, a vocabulary of materials and technology, what relationships or what tools we basically have, what resources we have to work with. When we combine those through the filter of, interestingly, economics and mass production, what we get is a solution to the problem of how we're going to house these families, right? So the kind of final causes, what we want the buildings to function as, the material causes, what we're going to make them out of, economics and production and distribution are how those are going to come together and actually engage the family themselves. Entenza commissions an influential set of projects called the case study houses, where he hires architects and builders to take some of the newly available materials, steel, aluminum, glass, concrete, and to think about prototype dwellings, literally case studies for what the post-war house might be. He commissions Charles and Ray, among others, to design one of these houses, Case Study House 8. And if you read the description in the magazine, for a married couple, both occupied professionally with mechanical experiment and graphic presentation, they're designing it for themselves, right? This is the Eames' own house. And you can see that they have a sloped site. It's in Pacific Palisades, so very near the ocean. And they go ahead and they design the house. They buy all of the material for what's going to be this kind of bridge to nowhere, right? This house that sort of sticks out from the side of the ledge. And as it's all on site, they have a change of heart, and they think actually that instead of cantilevering out from the slope, that the views and everything would be better, that it would be a friendlier gesture to the landscape if the house actually ran along the slope, right? So turned 90 degrees. And they have this kit of parts already. They basically rearrange it, and they design what becomes the iconic, today called now the Eames house, right? Not Case Study House 8, but we call it after the folks who built it and lived in it. So here is the steel frame. That is Ray and Charles looking sort of triumphant. And you can see that this is all just standard right out of the fabrication shop material. Open web trusses or open web joists, rolled steel columns and beams. You see the slope on the left that originally they were going to stick out from. Now they've rearranged it so that all of these pieces run in sequence along the ridge instead. The design is very, very simple. They have a little studio out back, a courtyard in the middle. On the ground floor, there's literally just a kitchen, a dining room, and a living room. Up above, there are 2 bedrooms, and there's a little stair in between with a toilet room upstairs, and then out in the studio as well. If the plan is simple, the elevations are really, really rich. And this is Ray taking what she's given as the kind of industrial base and finding just very, very subtle ways to ornament it, you might say. So panels of plaster or stucco, bits of color here and there, just enough to kind of engage the eye. And the steel is left completely raw, not covered, just painted. And so there's a sense that the sort of painterly aspects that Ray brings to the equation, the industrial aspects that Charles has brought to the equation, can actually coexist really well together. On the right, you see a detail. It is in California, so it doesn't need any of the insulation or anything that we're sort of used to here. The steel is literally, in some cases, the enclosure. But you can see that even though Ray and Charles aren't necessarily on the factory floor themselves, they are willing to accept what the factory gives them and to treat that as the basis for a new aesthetic. And here, a couple interior shots, you can see that they see the industrial box as a shell that they can then inhabit with their own stuff. And being great collectors, there's this like rotating set of fabrics and materials and furniture and sort of knickknacks that they find that they use to humanize what would otherwise be a kind of industrial shell. And this, I would argue, is among the most influential houses on the planet, right? We think about some of the more canonical works of residential architecture, like Mises Farnsworth House, maybe. But if you open an issue of Dwell today, a lot of what you see is basically the Eames house rendered in maybe different materials or with a slightly different compositional intent, but with that idea that we take industrial stuff and we inhabit it with the kind of knickknacks and things that humanize or warm things up. The Eameses could form an entire course on their own. They have a whole library of films. They do a whole set of exhibitions. They do design projects for other buildings that don't get built. The house is the only actual piece of architecture that they realize. We're going to jump ship here. I'll leave it to you to read some of the Eames readings on the Canvas site. But I want to return to Fuller, having looked now at Prouve and Eames and how they were a little bit more successful in taking the products of industry and finding new uses for them in the post-war. I want to look at what Fuller's post-war career was like, because it went on a related but really a very, very different trajectory. While Fuller is working for the government, while he's sort of borrowing grain bins to manufacture his Demaxian deployment units, he has also embarked on a project in cartography, sort of hobby of his that relates to the age-old problem of how you can make a flat map out of a curved Earth, basically. And Fuller hits on this idea that you could treat the globe not as a sphere, but as a geometrical object, in this case an icosahedron, that you could literally triangulate the surface of the globe And once you do that, you could kind of unfold it, right, and create a flat map that not only would be more accurate than the typical Mercator projections and things like that, but would also start to make you realize that we think about the world and adjacencies of various countries in pretty naive ways because of the way that our maps work. And Fuller produces what he calls the Dymaxion Air Ocean World Map. It has to have Dymaxion in it in 1944. Proves not to be an entirely new idea. Other people have done this, but Fuller is increasingly willing to sort of borrow ideas and label them as his own. And in 1944, he points out that, if you look at a Mercator projection, Japan, then our enemy or America's enemy in World War II, seems like it's on the other side of the globe, right? Far, far away. But if you unfold an icosahedral map of the world, what you realize is that Japan is a lot closer than you think if you go over the poles, right? So here in this map, here is Japan, here's the west coast of America. And instead of going all the way across the page, Fuller says what you realize is that the Great Circle route is much easier to see when you have an unfolded globe map here. And he says, really, when you think about it, New York and Europe aren't that far away, right? They just look that way when we use the Mercator projection. And he ends up going to Life magazine, producing a kind of printable version of this that people can cut out and see for themselves the various ways that you can rearrange the map to show, for instance, all of the land masses being contiguous or all of the oceans being contiguous, et cetera, et cetera. Fuller patents this, and if you notice, it's not an icosahedron, it's a slightly different shape that uses triangles and squares. This is because it turns out there is already a patent for an icosahedral map of the world, and so Fuller has to change the geometry slightly, and he gets away with this. The map is reasonably successful. It gets him in Life magazine. This is obviously something that is going to make him very, very happy after all the failures that he's had. But he also notices the geometry, right? And thinks about the fact that the icosahedron especially is a way of taking a sphere, which we know is a very efficient enclosure of volume, right? Least surface area for the most possible volume. And it combines that with triangulation, which we know is a very effective way of making structures. And Fuller begins to think about what happens if you take the Dymaxion map and treat it as a structural idea, right? A sphere that's an efficient enclosure made out of triangles that is an efficient structure. And after the war, after the failure of the Wichita House, he goes on to teach at Black Mountain College at the Institute of Design in Chicago. And he engages students in building these series of basically Dymaxion map structures, large scale. On the right, you see one of his early versions of this. He thinks there is something magical about taking those great circle routes and treating them as structure. The large scale version of that fails. On the left, one that begins to work, where he's thinking about those great circles as networks of triangulated panels. And then finally, in 1949, what he considers his first geodesic dome that he builds at Black Mountain College. It is maybe possible that he built an earlier one in Chicago at the Institute of Design. It's a little bit unclear where exactly this emerges, but you can see him coming out of what is recognizably a crude and not quite ideal geodesic dome there on the left. And on the right, his explanation for this, that you're taking the icosahedron, the 3D shape that's made up only of triangles, and exploding it onto the surface of a sphere and trying to get the efficiency of these two systems to work together. He takes this idea and basically becomes a sort of traveling critic. And what he does is he will go to a college and he'll propose that the students build a geodesic sphere onto which you could project the continents of the globe. So basically building giant Dymaxion maps. And as he does this, the grid gets finer and finer, right? The triangles get more and more regular. They get smaller and smaller. He tries various versions of this. The gentleman inside the dome on the right is a student named Kenneth Snelson, who has this idea about isolating compression and tension on surfaces and in structures. Fuller will, depending on your point of view, borrow or steal this idea and call it tensegrity. You see it being applied to the idea of lightweight spherical geometry on the right. And then finally, in the mid-1950s, Fuller patents the idea, and he calls it a geodesic dome. And the tricks that he basically claims are figuring out a way to triangulate the surface of a sphere on a very, very fine grain. This involves some pretty intense math, right? The geometry of the triangles has to change as they approach the main lines of the icosahedron. And if you look at a geodesic dome, you can find the large-scale icosahedron by looking for the pentagonal modules, right? So these areas that are right here, where the lines of the icosahedron come together, right? So that's a way of kind of rationalizing the surface. But really, he says that the impact of this is that it's going to give you a much more efficient way to enclose space or volume. And famously, the patent begins, my invention relates to a framework for enclosing space, which is essentially, you know, the whole history of architecture, like in one sentence. And he says that per cubic foot of volume, the sphere rationalized into a triangulated grid is going to be the most efficient way, the least pounds per cubic foot of enclosing a given volume. His patents turns into a genuinely successful company. Geodesics gets initially military commissions to build transportable shelters. So in some ways, you know, the same kind of needs that the military has for the splints that they commissioned from the Eames, the same way that the French government needs emergency shelters after the war. Fuller has a way of mass producing these. They can either fit on the back of a truck and get assembled on the site, as you see on the left, or they are lightweight enough that they can be built wholesale and carried by helicopter into place. The military is one major client. The State Department is actually another, and one of the applications that the geodesic dome gets used for is essentially a propaganda tent that flies throughout the Soviet bloc in this era of kind of cultural exchange. On the inside of it are all these kind of movies about how great American life is. On the outside is this symbol of American prowess, right? American technology, American inventiveness. Fuller gets corporate commissions. Ford hires him to enclose a pavilion in Detroit that they have had trouble building a roof over for 20 or 30 years. The geodesic dome is light enough that it can actually sit on the inadequate foundations that the original designers had. And for a long time, the largest span dome in the world, something like 600 feet, was this train car shed for the Union Tank Company in Baton Rouge. And so breaking records not only for the ratio of weight to volume, but also for just pure span. And all of these kind of come together in what is maybe the most famous of these domes, the U.S. Pavilion at Expo 67. This was right across from Fry Otto's tent that we looked at a couple of lectures ago. And again, the dome itself is kind of a piece of Cold War propaganda, right? Look how insightful or look how inventive American builders are. On the inside are all sorts of examples of American science and technology and culture. They have a spacecraft. They have all sorts of vehicles and things that American ingenuity has created. But really, it's the dome that strikes people as particularly amazing, right? It is almost, it seems like it's almost too lightweight, right? There's no interior structure. The dome is just this massive, very, very lightweight, almost cloud-like or web-like structure that surrounds the exhibits. It is covered in acrylic, and in fact, as the building is being engineered, the engineers realize that they have to design the foundations not only in compression but also in tension, that the sun heating up the air inside the acrylic dome is actually going to tend to lift the lightweight structure off of its base. It's interesting to kind of look at the details, right, and to figure out the kind of trick behind these. There's the geometric trick of sort of finding the icosahedron, but there is also the trick of fabricating it. And basically what geodesics would do would be to create 17 or 18 different connections that you see here at the center out of cast steel, in this case with little tabs sticking off of them. Those tabs would be drilled to accept piped or steel pipe that could be cut to length to form the triangulated grid of the structure around it. Again, the math was intense and required an awful lot of careful coordination. The detailing, as you see here, was designed to allow for plenty of tolerance, right? The pipes didn't have to be cut exactly to length. There's plenty of room in there for a pipe to be a little short or a little too long, and yet to actually work on site. After 1967, Fuller gets increasingly interested in the lightness of geodesics and sees these as a kind of metaphor for building in a way that doesn't impact the land so much, right? Treading lightly in addition to building lightly. He comes back to this kind of very naive set of ideas at the end of his career in what are often called the giant projects. He has this idea that as the domes get larger and larger, the proportional size of the individual members gets smaller and smaller. And he says if you were to build a dome that could enclose Midtown Manhattan, doesn't explain maybe why you might want to do this, but he says if you did, the members of the geodesic dome would be so thin proportionally that they would literally disappear, right? That you wouldn't be able to see them, your eye wouldn't be able to make them out against the sky. Whether that's true or not, he also took the idea of the dome being so lightweight that it was in danger of kind of floating off of its foundations in these projects for floating cities, where he thought you could build lightweight domes that would actually use the heating effect of the sun to kind of float through the atmosphere. Like the 4D towers, this is an almost impossibly naive idea. Bears mentioning, though, that the geodesic domes were delivered by helicopter, right? So in some ways, the promise of the 4D tower being delivered by airship, even if it didn't quite come true, like Fuller is certainly willing to, or certainly able to see that through in some ways, right? Air delivery of the structure. The influence of Fuller was profound and on all kinds of levels. In the 1980s, for instance, we found that there's a molecule of carbon. If you put 64 carbon atoms together in just the right way, they self-regulate into a geodesic sphere. And this particular carbon atom is called, not surprisingly, either a Bucky ball or its official name is Buckminster fullerene. There have been all kinds of promises made for this stuff that have never quite panned out. We've already seen how botany or biology has discovered geodesic domes at the smallest scale. And this patterning was certainly known even in the 19th century. This is Ernst Haeckel's woodcut of radiolarians who are building Buckminster Fuller geodesic domes long before Buckminster Fuller is even alive. Fuller himself went on to take the Dymaxion map and to do kind of these world tours on college campuses where he would do what he called world gaming, where people would actually play the role of either countries or like stakeholders in how resources got distributed around the world. And the Dymaxion map has gone from that first sort of 4D strategy map to the Life magazine map to this, where it is the kind of basis for this world game that Fuller sees as illustrating how wrong we have it as a planet when we distribute the resources that we have. And Fuller became this great guru of the early green movement, right? Not only for the sense that, you know, building lightly means building ecologically, but also for trying to see the role of design, not only at the smallest possible scales, as maybe the Eameses and Prouve did, but at the largest possible scales. And one final sort of point of interest is that these designers were incredibly influential in what we might call the high-tech movement of the 60s and 70s, something that we'll look at here in another week or two. They played often very specific roles. On the left, this is the jury for the Pompidou Center. You can see Philip Johnson in his seersucker suit, and the gentleman seated 2 spaces over to Johnson's right is Jean Prouve. That jury argued over which scheme to take, and I have no doubt that Jean Prouve was instrumental in getting Piano and Rogers the commission for the Pompidou. On the right, you see Bucky late in life preaching not to a college audience, but to an architectural office. The gentleman in the back is Norman Foster, and Foster was not only a Fuller devotee, but he actually collaborated with Fuller on projects throughout the 70s and even throughout the 1970s. Brought him into the office and really sort of tried to take on these ideas about lightness and eventually, as we'll see, about sustainability. Not that it was called that then. Fuller was more prone to use terms like ecology. But we will see how these designers, the Eameses, Prouve, Fuller, their ideas about how building performance and building assembly and production became intricately related and formed really this whole set of architectural languages a generation after their practices had flourished.